a relation and its FD set are given, and we have to decompose the relation into BCNF. For the relation to be in BCNF, the LHS or determinant part of each and every FD should be either candidate key or super key. And for the relation to be in BCNF, the relation should be in 2NF as well as 3NF. So, to check the given relation, to check if the given relation is in 2NF and 3NF, first of all we have to find the key for that relation. So, the given FDs are AB gives C and C gives B, and the key would be AB. Why? Because AB plus gives ABC. That means AB can derive all the attributes of the relation. Hence, key is AB. And the key attributes are, here the key attributes are A and B, and the non-key attributes are, non-key attribute is C. To check if the given relation is in 2NF, we have to check for partial dependencies. If the relation doesn't contain any partial dependencies, then relation is said to be in 2NF. So, first of all, we need to know what are partial dependencies. Partial dependency is nothing but an FD in which a non-key attribute determines, in which part of the key or partial part of the key determines non-key attribute. So, the first step FD is AB gives C. Here A and B are key attributes. So, this is not partial dependency. And second FD is C gives B. In C gives B, C is the non-key attribute and B is the key attribute. Hence, it is also not a partial dependency. Hence, the given relation is free from partial dependencies. So, the given relation is 2NF, is in 2NF. And to check if the given relation is in 3NF, we have to check for transitive dependencies. Transitive dependencies are nothing but non-key attributes to, if the FD contains non-key attribute to non-key attribute, then that dependency is called transitive dependency. Here first FD is AB gives C. Here LHS contains key attributes. Hence, it is not transitive dependency. And if we see the second FD, in second FD, LHS is non-key attribute and RHS is key attribute. Hence, it is also not a transitive dependency. So, we can say that the given relation is already in 2NF and 3NF. As we discussed earlier, for the relation to be in BCNF, the LHS part of each and every FD should be either candidate key, LHS, or determinant. Should be either candidate key or super key. So, if we see the first FD, here LHS is AB, which is the key for this relation. Hence, first FD doesn't, so first FD doesn't violate BCNF condition. If we see second FD, here LHS part is non-key attribute. It is not a super key. Hence, this violates, second FD violates BCNF condition. Hence, we have to keep these two attributes in separate table. So, the first table would be BC and the second table would be, here the remaining attribute is we have covered B and C, and the remaining attribute is A. And in order to maintain the relationship between the two tables, that is, in order to maintain the dependency preservancy, we have to include this C as foreign key in the second relation, in the second table, so that we can satisfy dependency preservation condition. Hence, the two tables are BC comma AC, BC comma AC. Hence, the correct option is option D. A program is given and we have to find out the output of the program. In this program, S is declared as character array, and the this return statement would return the value returned by the string comparison function. Here, string comparison function will compare the strings exit, and string comparison function will compare the strings yes and exit, and it will return the value accordingly. If both the strings are equal, then the string comparison function will return 0. This is the prototype of the string comparison function. It will compare its arguments s1 and s2, and if here s1 and s2 are strings, if s1 is less than s2, then string comparison function will return value less than 0, and if s1 is lexically greater than s2, then string comparison function will return value greater than 0, and if both the strings are equal, then it will return value 0. Here s is given as exit, so here string comparison function will compare the strings exit and exit. Here both the strings are equal, so this will return value 0, which is option B. Array of elements is given and we have to find the number of passes required to sort those elements by using bubble sort. For doing this problem, first of all we should know the working of bubble sort. Bubble sort will compare the pair of adjacent elements and it will swap them if they are not in the correct order. Here the given array is 62519. Here first and second elements are compared and they are swapped because they are not in order, so they are swapped. Next, second and third elements are compared and here also they are swapped. Next, third and fourth. So again third and fourth elements are also swapped because here 1 is less than 6, hence they are swapped. And here fourth and fifth elements are compared and they are in order, hence they are not swapped. At the end of the first pass, this would be the array and this would become the input for the second pass. Here in second pass, first and second elements are compared and they are not swapped. Why? Because they are already in order. So at the end of the second pass, this would be the at the end of the second pass, this would be the array and this would become the input for third pass. Here in third pass, first and second elements are compared and they are swapped. Why? Because here 1 is less than 2. So they are swapped. Next, third and fourth, second and third elements are compared and they are kept as it is. Why? Because they are already in order. At the end of the third pass, this would be the array. Here, the pass through the list is repeated until no swaps are needed. So, this array is passed through the fourth pass, and in fourth pass there will not be any swaps. Hence the list is sorted. So here the number of swaps would be 4, which is option C.